Welcome to the second part of the SystemC tutorial. In this tutorial, you will learn where to find SystemC designs and how to download them from the internet. You can find a link to the webpage that we have created that contains 13 SystemC benchmarks from our lab's webpage, or you can type in directly at your web browser www.s2CBench.org. This will take you to the S2CBench webpage that we have created in order to get information and allow anyone to easily download the SystemC package containing the benchmarks. If you go to, as shown in the screen, to the download link, you can easily download the package. Now, if you open the package, you will find 13 designs, or we prefer to call them 12 plus 1, and the main reason is that 12 of these are synthesizable. That means that if you use a commercial high-level synthesis tool, you will be able to create Verilog VHDL out of those 12 designs. There's one design, the FFT, which is non-synthesizable, and the main reason why it is not synthesizable is because it contains floating point operations and trigonometric functions, which are non-synthesizable as per Accelera's latest SystemC synthesizable subset. So the main reason for adding this benchmark is to help you understand how most of the commercial high-level synthesis tools or vendors basically support the synthesis of floating point and trigonometric functions. As their names say, the main purpose of these benchmarks is to test different commercial high-level synthesis tools and their capabilities. So that's why these are synthesizable benchmarks. What that means is that each of the designs that we have added to this benchmark suite allows you to test specific functions of the high-level synthesis tool. For example, if you look at the first design, the Quicksort, which is the simplest of all of them, it allows you to check if the synthesis tool allows loop synthesis, if a loop can be unrolled, not unrolled, or pipelined, array synthesis, functions, and pointer synthesis. If we go to a more complex design like the disparity estimator, it shows you and it allows you to check if your synthesis tool can do hierarchical design or multi-dimensional array expansions and so on. We have also uploaded the benchmarks to source.forge.net because we have seen that some people were having problems accessing our webpage, especially from mainland China. Once you have downloaded the package and you have transferred them, in this case we're going to use a Linux system, you have to unzip it. In this case you can use any the tar utility in Linux. You can unzip the benchmark suite and you will see all the different designs with the files included. That includes the SystemC files with the test bench and the test patterns. So in this case we're going to go to the FIR filter and we're going to compile that design first. So now we can change to the FIR directory. We can see all the files in a package and we're going to open the main.cpp. Every test case contains a main.cpp, which basically declares and instantiates the unit under test, in this case the FIR filter, and the test bench that is basically responsible for reading test patterns from the external files and then applying these to the unit under test and reading back the results and comparing them against the golden output. So you can see here the declaration of the FIR filter in the test bench. We can now continue looking at the rest of the files. We can open the FIR, the FIR.h, the header file, which contains the SC module. This is the entity of our SystemC, of FIR filter in SystemC, with the input and output ports, and the constructors and all the threads of this module. We can open the FIR.cpp. It contains the functionality of the FIR filter, which is basically one loop with the sum of products of the different tabs of your FIR folder. You can see the variable declarations of the main thread, the FIR underscore main, and the main loop that does the sum of products. Well, the main step after we have reviewed the files will be to compile these. For that, each of the test cases comes with a makefile that includes all the source code. You only have to modify, as we showed you in the previous tutorial, the path to the SystemC libraries, and then you just call make in order to compile the benchmark, as shown on the screen. Once the compiler G++, in this case, is finished, if it's successful, it will generate a binary file. As we've shown here, it creates an fir.exe file, the binary which you can now execute in order to simulate the FIR folder. You can also have the option to create a waveform to dump a waveform in VCD format, in value change format, and then you can use a waveform viewer like GTK Wave to see that. This case you can make clean the previous compilation, then you make wave, you call make wave, and it will create another exe file. When you call this, you execute this binary, it will create now a VCD file. It runs the simulation correctly, and then it creates also a trace underscore behave.vcd. You can now call GTK Wave, in this case a free open source waveform viewer, and you can see the waveform of the simulation as shown on the screen. Once GTK Wave opens, you can select the signals that you want to trace. Now the signals that actually can be traceable are basically have been defined in the main.cpp. So if you want to trace internal signals, you can add those in the main.cpp file and then recompile the SystemC files and run them again. In this case, we just declared the input and the output ports in order to trace these. This completes the second SystemC tutorial. We hope you enjoyed it, and if you want to know more about SystemC or S2CBench, please drop us a line or write a comment on the webpage. Thank you very much for your time.